About a week ago, we started talking about question number 2. This problem that we have that I gave you guys from a practice exam, from a AP practice exam, and we did part A and part B. Now we can do part C. Now that we know how to find the volume using cross sections. So we have two regions, region R and region S. We know that the two functions are y equals 3 minus x squared and y equals 2x. And we are asked, part C, the region R is the base of a solid. For this solid, each cross section perpendicular to the x-axis is an isosceles right triangle with one leg across the base of the solid. So one leg across the base of the solid. Also, another thing to underline was that these cross sections are perpendicular to the x-axis. What you have to do is write, but do not evaluate, an integral expression that gives the volume of the solid. So to start this off, I still want to help you visualize these three-dimensional figures, and I still want you guys to draw them. Even though on the AP test, I do not want you to spend time drawing them. On the AP test, you will not have to draw a figure as part of your work, so you shouldn't spend time drawing it on the AP test. However, since this is still fresh, new stuff, and the hardest thing that students find is visualizing the solids, I still want you guys to practice drawing them. So I'm going to help you draw what this solid looks like. So we're focusing on region R, which happens to be the region that I've highlighted in yellow. And as I'm prepping to draw the three-dimensional figure on the x, y, z coordinate plane, I also shaded region R in yellow. And what we're supposed to do is we're supposed to show cross sections perpendicular to the x-axis that are isosceles right triangles with one leg across the base of the solid. Okay, so the way that looks, a lot of you guys are used to seeing isosceles right triangles, maybe something like this. However, if we want one leg across the base of the solid, we don't want the base to be the hypotenuse. What I'm going to do is I'm going to kind of rotate this so that the leg is the base, or one of the leg is the base. That'll make the other congruent side the height. And we have something that looks like this, where the base and the height are equal to each other, because those are the congruent sides for your isosceles right triangle. So if I take this base and I go ahead and place it on my x, y, z plane, making sure that it runs parallel with the y-axis because it has to be perpendicular to the x-axis. Okay, this line here represents just the leg, one of the sides of that triangle. Okay, if you look at it in your 2D, that's pretty much what I've drawn here. Okay, so here's my 2D, this is my 3D. Okay, so then the height, so this leg, the height would look like this, and then the hypotenuse will look something like that. This is the right angle here. Okay, so let me try to fix this a little. Okay, and hopefully this looks a little better. So I should have drawn this height more of an angle. I'm trying to give it that illusion that it's popping out. Okay, so I'm trying to make these triangles, give them the illusion that they're popping out. So I had originally drawn it. I had originally drawn the height pretty parallel to the z-axis, and to give it that illusion, I probably should have made it more at an angle, made it pop out a little more. I blame my poor art skills on that, but it should look something like this. Now, if you're looking at the 2D version, this is popping out, so it's popping out to you. So in 3D, I'm trying to give it the illusion that it pops out. We're looking at it from an angle, and it's popping out. And in 2D, it's coming towards you. So the z-axis comes towards you, so these are popping out towards you. So these congruent sides happen to be these congruent sides here. Okay, so that's how this isosceles right triangle looks like when it's on the region R. The base is one of the legs, and it is perpendicular. That leg is perpendicular to the x-axis. Okay, so we're pretty much ready to write, but we will not evaluate the integral expression. So what we need to remember here is that the area for a triangle is base times height divided by 2, or 1/2 base times height, however you learned it. Okay, so there it is. Area is equal to 1/2 base times height. The nice thing about this isosceles right triangle, the nice thing about it being on the side or with one of the legs as the base, is that if we find the base, if we can find an equation that represents the base, then that's pretty much the height also, because the base and the height are congruent. So in other words, if we can find an equation for the base, when we plug it in to find the area, it's just squared, that equation squared. So let's start off by writing the equation for the base, writing an equation that represents the base for this right isosceles triangle. Go ahead and pause the video and see if you can come up with the area, an equation for the base. So go ahead and do that now. And all you really have to keep in mind is that concept of the upper function minus the lower function. So it's easier to see on the 2D, the upper function minus the lower function, because we are integrating with respect to x. We do the upper function minus the lower function. So that is an equation that represents the base for this isosceles right triangle. And I just said that if we can find an equation for the base, that'll be the same as the equation for the height, because the base and the height are congruent, they're equal to each other. So the area, oh, I forgot the 1/2, would be 1/2 times 3 minus x squared minus 2dx squared. Okay, and all we have to do is plug it into the volume, to the volume formula. And in calculus, the volume, finding the volume with known cross sections or given cross sections, volume is the integral from a to b of a of x dx. Notice that there is no pi. This is not a solid of revolution. We are not dealing with disk method or washer method, nothing like that. This is cross sections, volume with known cross sections. So this is the formula they're going to use, and just plug in your givens. Keep in mind that I do have the information from my last video. So the intersection that we calculated when we worked out part A and part B, there's this intersection also. So we're going to use that to set up our answer for part C. Go ahead and pause the video, see if you can get the setup. And since we are dealing with integrating with respect to x, we are looking at the x values for our limits, so that negative 1.636576 and that positive 1. So your answer should be something like this. Should look like this. Keep in mind that that 1/2 is a constant, so that 1/2 can be placed outside of the integral. So you can take it out, take out the 1/2. Okay, so that's the answer for part C. Now what I'm going to do is I'm going to show you the rubric. And notice that part C alone would give you 2 points. 1 point for the integrand, 1 point for the limits and constant. And part A and part B gave you the most points. Part A was 3 points. 1 point for the integrand, 1 point for the limits, and 1 for the answer. Part B is 4 points. 2 points for the integrand, 1 point for the limits and constant, and 1 point for the answer. So this was out of 9 points, and for the most part, the FRQ problems are out of 9 points after you have added up part A, part B, and part C, or how many ever parts they are. The total should be out of 9. Okay, that's pretty much what I wanted to discuss in this video. Hopefully this helps. That'll conclude the video.